Well, thank you very much. Actually, I'm extremely happy to be here. I mean, especially to celebrate the life of Dean Lytle. And it was actually a joy at lunch to have dinner with Marilyn. Lunch, sorry, with Marilyn. I don't know if we're having dinner tonight. Anyway, so I'm very, very happy to be here. I should also say that I'm over 35 now. But that was just last month. So anyway, okay. So today I'm gonna talk about embedded optimization in smart products and systems. And so I'll talk about what it is and how it works, and we'll look at some applications and things like that. And I should say, I had a lot of help from a couple of former students and a current student, Neil and Young, helped me put this together. So I'll just jump in and let me first I'll tell you what you're in for. So the good news is there will be no equations. Actually, there's going to be one, just one. It's going to be non-technical. So that's the good news. Now I'm going to focus on ideas. So hopefully you'll leave here with some idea about how these things work. What are they and what do they do? Not, of course, technical details, but kind of, how do they impact your life and that sort of stuff. Now the bad news is this. I guess maybe a better public lecture is one where you have cool videos and stuff like that, and everybody goes like, oh, that's great. Anyway, I'm sorry to report, there won't be any. Sorry. So, but we're going to talk about ideas, and hopefully you'll get some of an idea about it. It's non-technical, and I should say that I have spotted some faces I see in the crowd who are technical, and I should just blanket apology to them ahead of time, because if you know anything about anything I'm going to say, you're probably going to cringe, okay? But too bad. Okay. All right. So what I'm going to do is this. I'm going to start and just talk about, what is a smart system? What is a smart system? I'll talk about optimization, and what is it? How does it work? How does one do it? I'll then talk a little bit about recourse, which is the idea of doing something different once you learn new things. So we'll talk about that, and I'll just wrap up. So let's start with just what is a smart system? What do I mean by a smart system? This is not the universally acknowledged term, okay? But I think it's a perfectly good one. So the idea is this: a smart system is one. It's a system that takes a sophisticated mathematical algorithm, right? We'll talk about that. It runs on one or more computers or devices. This could be your phone. It could be a giant data center. It could be any of these kinds of things. And it works with lots of data, and it makes real-time decisions. Okay, so that's what it is. Now let's look at some examples. So a quick, just an obvious example is power generator dispatch. So you have generators generating electrical power, and what happens, or I know exactly how it happens in California. I imagine it happens in a very similar way here. And the way that works is something like this. In California, between like midnight and 2 a.m., what happens is in a bunker in Folsom, a bunch of computers run, and what they do is they predict the demand for tomorrow in California. That's the first thing they do. And the second thing they do is they schedule the generators. There's maybe 3,100 generators, and they'll tell each one, you're going to come on at this time, and you're going to generate this amount, and at 2:15 you should adjust your power. It's this kind of thing. And the idea is you want to meet the predicted demand. That's sort of the idea. You want to minimize total cost. I mean, you wouldn't use the most expensive generators first. You'd use them last. Of course, you have to respect limits on the transmission line capacity, right? So there may be not enough transmission capacity to get the cheap electricity from one place to another. So these are the ideas. And the other thing, this is very important, is you have to have contingency plans for unplanned outages, right? So you'll always work out, you'll have some standing by just in case some big generator goes out or something like that. So that's an example of a smart system. Now, just to give you a rough idea of just to get a picture associated with it, here's a picture. A map of the US showing a bunch of generators. There'd be the ones in California. And it doesn't matter, but this would show you a detailed map. I realize in the back there's no way you can see any of this. It doesn't, actually, I can barely see it myself here. So, but the idea is that you see a network of, a whole bunch of lines, maybe 10,000 major transmission lines, and that's where the power flows over those lines. This is just to give you a rough idea. Okay. Now that works something like this. There's actually a website in California you can go to, and you can log on, and it'll show you tomorrow's prediction for usage. And it's based on a lot of things. It's based on, not that many actually, it's based on history, historical data, and it's based on weather predictions for the next day. Okay, so based on that, so this would be an example here. So this is time, that's a 24-hour period. This is the middle of the night. And this is the predicted demand, the white curve here. That was predicted, well, the night before at midnight. And the red curve shows you what actually happened up to when this snapshot was made, which was about 7 p.m. Now the axes here, that's 22 gigawatts, and that's like 40 or something. So the conclusion is the predictions are pretty good. They're not perfect, but they're pretty good. So that's the idea. And so here's your curve, and between midnight and 2 a.m., you coordinate with all the generators to try to figure out how are you going to generate that much power at 6 p.m. tomorrow. Okay, so that's the idea. Okay, second example. Oh, and by the way, one of the themes here is that these ideas are used in a huge variety of areas, right? And they're areas that don't look the same. And in fact, if you took someone from one of these areas, introduced them to someone from the other area and said, hey, you do the same thing, they would be either very angry or, but they would certainly say, no, that's just not possible, okay? Or they wouldn't like the idea. Okay, so our next example is a quantitative trading engine, so like a hedge fund. And so the idea is something like this. On a minute-by-minute basis, by the way, that could be second by second or day by day. I mean, that's just arbitrary. What you do is you determine the trades to make. And of course, what you want to do is you want to maximize the expected return. You can't possibly maximize the return if you know the return. Well, you don't. Let's just leave it that way. Now, some people get close to it, but you don't. And of course, you want to respect risk and leverage limits, right? And there might be other limits, like if you're running a mutual fund, you can't have short positions. I mean, for example, okay? And you'll use the current estimates of returns, risks, and transaction costs. So this is the idea. So once again, your data is coming. You have data coming in. You do some thinking. I mean, a big computer does some thinking, and then out comes a list of actions, which are trades. Okay. So this would be the kind of thing you might want to see. These are actually real. So, I mean, it doesn't matter. But these are real. And this might be something like the cumulative return on a unit investment, and that might be the Standard & Poor's index. And then what you'd like to see is something like, if you do this well, then it might go something like that. And notice that it goes down, so you don't always win, of course. But the idea is sort of on average. So this is the kind of the picture you have in your mind, right? And if you could do this, that's 250 days, so that's a trading year. And so the idea is if you can do this year on, year after year, that's very good. That's the idea. Third example, spam filter, right? So, I mean, notice that they're actually quite different, right? The power generation dispatch, your picture in your mind should be gigantic machines and turbines and big dangerous things and high voltages and things like that, big powers. Trading engine, it should be something like a bank of computers sitting in New Jersey or Connecticut, something like that, or the Midwest. Spam filter, well, that's distributed. We'll talk about that. But here's the idea. An email message comes in, and you examine the attributes of the message. And that might be things like, where'd it come from, number one. What are the word counts? You might have something like 10,000 words that you use, and you just count the number of times each of those words appeared in that email message. You could guess some of those words, but I'm not going to say them here. So that, and then, by the way, most of these word counts would be 0. Okay, they'd mostly be 0. So what would happen is you'd look at these attributes. You might have 10,000, 50,000, 100,000, something like that. And based on that, you'd combine that with data from lots of other people, and then you'd guess if it's spam and flag it. So that's the action that you take. Okay, and this, this is kind of obvious. You might, look at like sort of where it came from, and there would be things like this, inheritance funds and receive your payment. These would go into this list of the word counts and sets of word counts. Okay. Well, there are lots of other examples, and I'm just going to tell you a little tiny bit about them and list a bunch. One is engine control. So, which is weird, because if in engine control, what happens is maybe 50 times a second, you make predictions of how much power you need at the wheels. You predict that, you based on all sorts of things. You predict how much power is needed. You do things like you're examining various fuel flow rates and things like this, torques at various places, and based on that, you're adjusting firing injection angles. And this might be 50 times a second, something like that. What's strange, I mean, that's of course normally what people call automatic control, but it's not much different conceptually from scheduling the generators for California the next day. It's just not that much different. It happens on a much faster time scale, and it's much simpler calculations, right? You're not doing huge calculations. You're doing a little bit of calculation in 20 milliseconds. Same would hold for a hybrid vehicle. So in a hybrid vehicle, actually, you would think, oh, you just have a battery there. What could be so hard? You charge it when you can, and I don't know. That's actually not right. If you have a hybrid vehicle, the whole point is this. If you don't want your battery full. So if you think about it for a minute, what you really want is this. In a hybrid vehicle, when you go down a hill, you need somewhere to put that energy. Otherwise, you're going to be using your friction brakes, and it's just going to be turned into heat. So the worst thing that could happen to you would be have a full battery and then roll over a hill and go downhill like that, and you have nowhere to put the energy, right? Now, the opposite is true. If you all of a sudden need a burst of power at the bottom of a hill, the worst thing that can happen is have you empty, right? So it actually does take a little bit. You have to think about these things. Okay, a recommendation engine. Well, we've all seen that. That's something on Amazon or Netflix or something. And you examine the actions of millions of people, and then you build a model, and then it says, hey, other people, you might like this movie or something like that. Okay? So a search engine is actually no different. It's the same thing. You take lots of data in, and you do this. Online advertising. So basically, almost all online advertising is now done in a very sophisticated way, where you make guesses about whether someone's going to click on something or not. And then you have several choices of what you show, and it's not as simple as showing the one that is most likely to be clicked on. It's not. So it's quite sophisticated. Flight management system. That's an example where you go into a modern airplane now, and you simply type some stuff into a flight management system, and actually, once it starts, it'll fly from airport to airport. Maybe not so well. I think it doesn't take in the flaps or something like that, or the slats, but it basically will fly. It'll fly to a waypoint that you've programmed. It'll execute a flawless turn, a turn better than any human pilot could do. Okay? It won't, and it's going to be coordinating, all the control surfaces. It'll be changing the thrust, all sorts of stuff that basically a person couldn't do. Okay? That's an example of one of these. Automated real-time fraud detection. That's running everywhere. We're all subject to it. Every single time you make a credit card transaction, what will happen is various attributes of that transaction will go to a central computer, which will very quickly, one hopes, guess whether or not that's fraud or not. And if it thinks it's fraud, it's going to block it, right? So that's what will happen there. Okay, supply chain. I mean, this is just amazing stuff. Modern supply chains are very sophisticated. I mean, so for example, well, it's a good example for where we are. But in the Bay Area, for example, I mean, I assure you right now, Amazon stuff is arriving in warehouses that no one has ordered. No one has ordered it. It has been predicted that these things will be sold tomorrow, and they're being forward cached in warehouses. So there's a warehouse in Milpitas. There's stuff arriving right there, right now, that 25 people in the Bay Area don't even know they're going to order. But they are, right? And you know what? If 20 of them order, that's fine too. And if 30 order, that's fine too, as long as you're one of the first 25. So anyway, so things like that, I mean, these are all like, they're pretty amazing. A lot of these things are hidden. You just don't see any of it happening and all that kind of stuff. It is all happening. Oh, last example, revenue management. Does anyone know what that is? Okay, I'll tell you what it is. That's a euphemism. That's a euphemism for companies extracting as much money as possible from you. That's what it is. And so when you get on an airplane, right, and they release seats and stuff like that. I mean, so if you, by the way, this is great for companies, just so you know. So not so good for us. But basically, you release a seat at one thing, and what they're hoping for is a business person who looks up and says, oh no, I have to be in Chicago tomorrow. And then United in San Francisco will say, oh, well, look at that, we have a seat, but it's kind of expensive. Anyway, you get the idea, right? So now the decision you have to make there is whether you release this expensive seat or not, right? Because if you release it, and because, oh, by the way, if you don't release it and you fly empty, that's silly because you could have put a college student in it who would have paid you something, right? Right? So, and if you release it too early, I mean, the worst thing that could happen is you say, okay, that's it. You release it to the college student, and then 5 minutes later, business person shows up and says, with a big wallet, and says, I absolutely must be in Chicago tomorrow. Anyway, you get the idea. Okay, so, all right. So, what does this talk about? It's about this. How do these things work? You know, not the details, of course, but down to the 5,000-foot view, and we'll see how they, we'll get a look at this. How are they similar? What methods do they use? How do they fail? Like, when do they fail, and how do they fail? And they do fail, sometimes spectacularly. And then, where's this all going? I don't know. I'll tell you the answer right now, but okay. So let's start with optimization, because this is all based on something called optimization. Now, the idea is, it's mathematical optimization. By the way, if you just say optimization to normal people or a random person, it means search engine optimization, because that's such a big deal, right? So you have to specify mathematical optimization. And the idea is you use math and computers to make good decisions and choices. And I mean, this is, I guess, I'm not sure who coined this term, the science of better, but boy, whoever it is, that they were well paid. Because it's just a great term to describe it. Now, it's old, right? This goes back to like calculus. That's kind of what calculus, and if most of you, many of you, I presume, were tortured by being forced to take calculus. By the way, some of the torturers are in this audience right now. Anyway, but we're not gonna, I don't want any mob actions or anything. So the point is, this goes back to like Isaac Newton, and Gauss and Leibniz. It's calculus, right? And the picture you have in your mind, that is, if you have not successfully suppressed those memories, the picture you have in your mind is something like this, and you're looking for this point that has the lowest cost. And then I told you there'd be one equation. That's it. Okay? So there it is. It's like now, the point about all this stuff, this is 19th century, and by the way, 18th century and even 17th century. But the point about all this is, if you think back on the calculus that you took, you know what? No one is ever going to come up to you and say, I have a rope of 50 feet long. If you lay it on the ground, I'll give you all the land it encloses. How do you do that to maximize? I mean, that doesn't happen, okay? I mean, it happens in calculus classes, and it doesn't happen anywhere else, okay? So, all right. Now, there's a new style. And actually, that's actually the second sub-theme of this. So the first theme is that these ideas cross all these application areas, even to the point where the people who do them would hate to think that they're connected, right? But the second is there's actually a new kind of math emerging. I'll talk about that. So it's this new style. New means new, like post-Newton and Leibniz and Gauss. Okay, it takes an algorithmic approach, and it uses computers, right, and lots of data. So that's this new style. Now, the history of that goes back to von Neumann, right? So that'd be about, the 1948, which is coincidentally roughly the year that people would say is when modern computers were sort of invented, although that also, goes much earlier. And there are people like Danzig at Stanford, a colleague of mine, who looked at, using optimization on a computer, right? These were very crude computers. And so if you wanted a picture there, if you wanted a picture of this new style, it wouldn't be an equation. It would be something like some source code here that is expressing, that happens to be, that's a finance problem, okay? And it's saying, please find the best portfolio. And if you wanted a picture to put in your mind, it would be something like a data center. By the way, if you know about data centers, you know that that's way old. So, but anyway, but as a picture, it's just fine, okay? So let's talk about optimization, how it works. Well, there's a couple of pieces, and I'll tell you what the pieces are. The first is there are some things called variables, and this is what you want to choose. Some people call them decision variables, right? So it'd be things like, how much of each asset should I buy? Should I sell this now? Should I flag this as spam? Should I advance the fuel injection time? Or should I retard it, right? These are the things that you're supposed to choose. And you have to have a list of things that you care about. They have to depend on the choice. If they don't depend on the choice, it's silly, right? So, and then you need a model of how what you do affects what happens, right? So that's the other critical part. And then you have to have a description of your preferences among the choices. So we have to be able to say, if this happened, would it make you happy? How happy would you be? How unhappy would you be? This kind of thing, right? And so these are basically the parts. There's no other part, just these. Well, let's see how this would work. For generator dispatch, the variables would be the generator powers. Like, should you be generating 20 megawatts and you 15 and you 0 because you're too expensive, for example? You have to respect, here are things you care about. If the limit of that generator is, 20 megawatts, and I say, please generate 25, it's ridiculous. It can't happen. So then you'd have to say you're very unhappy with that, right? Because it's just impossible. So you have to respect generator limits. You can't overload transmission lines. You have to meet required demand. Not always, but that's a pretty high up there goal. You want to minimize the total cost. You might care about minimizing CO2 emissions, all other things being equal. And then the model would describe how power flows in a network, right? If I set this generator to generate 20 megawatts and you're generating 18 and I hook it up, where does the power go? I mean, what happens, right? And then you'd also have a model of the cost of generation, for example. Now, to describe preferences, this is done many ways, right? But one way is you have hard constraints. That just says that choice is completely unacceptable. It is unacceptable to ask that generator generate more than it possibly can, right? If you are a mutual fund, you are not allowed to have a short position. It's not legal, period, okay? So then you have an objective function, and that measures desirability. And different fields use a cost function. A lot of people in engineering minimize costs. And then people in economics and finance typically maximize utility, or more directly something like profit, or something like that. And then, depends on the field. There's actually no difference, although there's all sorts of jokes about pessimistic versus optimistic fields and so on and so forth. But there's no difference, right? Because I could just as well maximize my negative cost or something like that. Now, there's other methods to do this. There's things like you can talk about satisfaction, or you can have a trade-off. That's actually very common because all these things involve trade-offs. Okay. Now, generator dispatch, your constraints are you have to respect the limits. You can't overload transmission lines. You have to meet required demand. The objective is minimize total cost of generation and minimize CO2 emissions, right? And you might end up with a trade-off curve that looks like this, that says this is what's possible. And so, for example, I could get very cheap power over here by burning, hideous coal or something like that, super dirty coal. But the point is here, that's going to come at a cost of a very large CO2 output. I could also operate up here, right? By the way, operating up here is just called, there's a technical name for that. It's called stupid, right? Because then you're actually, what you're doing is you're generating power. It's expensive. And you're spewing lots of carbon dioxide out. So that's, I'm sorry, I shouldn't have used the technical term. Anyway, so, okay. Okay, trading engine. In a trading engine, the variables would be how many shares of each asset should you buy or sell. That's what it is. This is what you're trying to figure out, what to optimize, right? By the way, the answer here could be nothing, right? If you're going every 10 seconds, then very often the answer is do nothing. But that's a choice, okay? The constraints is to respect legal requirements, broker requirements. You can't actually go too far short without somebody coming after you. And the objective would be to maximize the average return, net the transaction cost, and to minimize risk, something like that. And your model connects your portfolio to the risk and the expected return and the transaction cost. These would all be part of the model. And so this one is real. So this would be a very conventional thing. It would show you that here's a bunch of portfolios where this is more risk, and then this would give you the mean return. And it's a trade-off, and you can operate anywhere you like down here. So these would be presumably something like T-bills, although given recent history, I'm not sure that that should be at the 0% risk. So this would be the type of thing you could do. Okay, spam filter. The variables here are actually quite different, and it's interesting to think about. So in a generator thing, variables correspond to big actions, right? When you choose something, some gigantic turbine fires up, or it changes its power tomorrow at 2:15 p.m., right? Giant powers go on. The lights in Los Angeles turn on, right? Big things happen. Here, if you're doing a trading engine, when you choose what your variables are, things happen. Packets go from your server to the trading server that say, please buy me, quite a lot of this, and by the way, I'm also selling this, and a little packet comes back. This happens very fast, by the way. A little packet comes back saying, done. Okay? So basically, your variables are in both cases are like actions. Here, it's very interesting. They're not actions. In a spam filter, the variables are parameters in a statistical model, right? And this is a lot of things. So they're not associated with an action. They're just parameters in a model. And the objective is you want to minimize, well, the false positive rate and the false negative rate. And the model is going to predict how these depend on these parameters in a statistical model. And you might get a trade-off curve that says you could operate over here with, that would be 0.2% false positive rate. But unfortunately, in that case, you'd have to be OK with a 1.2 something or other percent false negative rate. Okay, so this would be, this would be the type of thing you would imagine. You could operate anywhere along there, right? So, okay. So it's time to actually do some optimization. We're going to do some. So, all right. We're going to do generator dispatch. And we want to schedule for 200 megawatt hours of demand. And we want to minimize total cost. We have 4 generators. Each one will generate up to this amount at this, over this hour. And that's the price. So it's 37 cents, $37, 39, 43, 48. Okay? And what's the answer? What should you do here? Yeah, you should, well, you're looking for 200. You should go for the cheapest first. So you'd use all of this one. You'd use all of that one. You're up to 190, right? And then a little bit of number 3. And that's going to minimize your cost. Okay? Everybody got that? So guess what? That's right. And you know what? It turns out a lot of optimization problems are just like this. Common sense just works. They're not that hard. If you have a handful of variables and they're not coupled in complicated ways, it just works, right? Like if I tell you, which of these products do you want to buy? They're identical, but, here are the prices. You're like, doesn't take long to think about that. And, so, a lot of it just works this way. So these are easily solved by a person using common sense. So that's, that has to be admitted. But it turns out it takes very little before a human being can't do this. Very little indeed. You just add a few more complexities and the humans are out. Okay? So, for example, you just take our little example here and we have the generators here. Then we have the demands are out here in red. And it's the same thing except that 200 megawatt of demand is distributed across these outer nodes. And then all of these are transmission lines that have maximum capacities. And so now, guess what? It's not simple. No human being can do this, I assure you. No human being can solve this problem. Because what's going to happen is, that's the cheapest one, and you'd like to use all of it, but it turns out you don't have the transmission capacity to get it all. And so you're going to have to be forced to get more expensive ones and all that kind of stuff. And it turns out, well, it's not so easy, and in fact, it's simple. People can't do this. So the solution might end up looking something like this. That first one, which is the cheapest, it's offered up to 110 megawatt hours. You can only take 91.3 because you don't have a way to get it from that generator to the people who want it. Okay? And you can do all sorts of stuff with this. The second one you can use at full, and you're even forced to go to this fourth one, which is the most expensive one, right? And then one of these lines might be congested. It would be at its capacity. Other ones would not be. By the way, this tiny problem here, a computer can solve in about 20 microseconds. This is nothing, right? On my laptop, I can solve a problem like this with thousands and thousands of generators and thousands of transmission lines. And it goes without saying, people are totally out in a situation like that, right? Okay, so let me talk a little bit about where models come from. First of all, they come from physics, right? I mean, well, that's kind of the point. First principles, right? That's, I mean, since Newton, right? And that's great for generator dispatch because we've known for a long time how power flows on transmission lines. We know how that works. And the models are actually extremely good. They're certainly accurate within 1% or something like that, right? Good enough for that, and that's fine. But for spam, so if someone comes up to you and says, I have a deep mathematical model of spam, you should turn around and walk the other way because it is nonsense, right? Now, the truth is, in some fields, people start their story by pretending they have a deep mathematical model for it, or like they're independent samples from some distribution or something. By the way, you should not turn around then and walk away, because you should ask that person, you don't really believe they're independent samples, and the correct answer, if they say, oh, yes, they are, then you walk out. But they should say, the correct response is they should say, oh, of course not. Spam, you know, the spam is made in you know, Russia and Romania, and it goes through you know, people's computers in Florida, and you know, whose computers have been taken over. That's what spam is. It is certainly not something from a distribution. Okay, but so the point is, there's no basic fundamental mathematical model of it, right? So the other main way to get a model is by data fitting. So you guess a form, and then you fit parameters. And what's weird about it is, guess how you fit parameters using optimization. So it gets kind of weird because you ask Google, what are you doing? You say, I'm serving an ad on a web page. How did you choose that ad? And they go, well, optimization. And you'd say, well, based on what? You'd say, oh, the probability someone's going to click through on the ad. And you'd say, well, how did you get that? How did you get that model? And they'd say, optimization. I mean, look, it looks kind of, it sounds circular, right? I mean, it's weird. Okay. So it turns out that this business of using different model styles, it's a source of tension and confusion, and it's actually why people who do primarily this kind of stuff and people who they generally don't like each other. Or they're very suspicious of the other, right? You know, this kind of thing, right? So, and it's weird because you have people in physics, you know, you say, what are you doing? And they go, well, I'm really working out how the world works, you know. It's like, well, actually, the truth is they are. I mean, but, you know, and then the data fitting people are the same, like, you know, let's put the physicists on the spam problem and see what happens. So, okay. All right. So first principle models, these would be things like space, you know, Newtonian mechanics, right? Electricity transmission. And these are, you know, generally written as equations, and they can be assembled from smaller things. So you can hook them together and then figure out what happens. Now, fitting a model, this is something probably you also saw in the calculus course, which you may or may not have successfully repressed the memory of. So that's this. So here's the very common example is here's a bunch of data. Here's like one variable, and then here's some other variable. And the blue dots are like the data. And you just, everyone has seen this. You may have seen, I mean, you did see it in the calculus class. You may have repressed the memory. And so you fit a line through it like that. Now, this line has two parameters. Okay, it's got like a slope and an intercept. Okay? So, however, the way real big models are done is kind of the same. By the way, people who actually do this are probably cringing right now. It's more or less the same, except instead of two parameters, you have hundreds or millions of parameters. And it's nothing you could do with your eyeball like this. Okay? And that's actually the key to using optimization in applications with non-existent or dubious first principle models, right? So that would be the key. You'd say, you make up a model for spam, and someone says it's ridiculous, and you go, well, I just fit it to 100 million data examples. And then you'd say, okay. And then the question is just, you know, you check, does it work or not, right? Okay. So I'm going to talk a little bit now about pitfalls and complications in optimization, right? Like, what can go wrong? I mean, at this point, you should be thinking something like, wow, optimization is great. You can do anything from run a car to spam filtering to this is fantastic. We should all be doing it or something. I don't know. So it turns out it's not that simple, right? So let's look at it. So first of all, the first thing is, you know, you can formulate optimization problems all you like, but you can't solve most of them. I'll get to that in a minute. There's other stuff where there's stuff you forgot to specify. And then, of course, there's the issue of bad models. So I'll go over these a little bit, quickly maybe. So you formulated the problem, and then the next question is, can you solve it? And it turns out how hard it is to solve a problem depends a lot. It depends on the size. If it's a little problem with a handful of variables, no problem. But if it's a problem with 100 million variables, different story. But it also depends very much on their mathematical characteristics. And it turns out, and this is the closest I'm going to get to what I do, it turns out there's some really simple-looking problems that are actually really hard to solve. And conversely, you have the following. You have some super hard-looking problems. They look like really hard, like, generator dispatch, and it's all coupled together, and if you use some of the transmission line, then you can't, and all this crazy stuff. Those are actually extremely easy to solve. These things are not obvious. And that's what I'll be talking about tomorrow. And there will be equations tomorrow. So I have a certain amount of equations that have to come out, daily. Today, they're not all coming out. Actually, tomorrow's allotment and today's will come out. So, okay. All right. So the other thing is this. It turns out in optimization, you have to say exactly what you want, right? So another way to say it is these solvers have no common sense whatsoever, right? None. And a negative way to say it, which this comes up so often, is you have absolutely no right to complain, no right whatsoever, about what comes out if it's something you didn't specify. If you say, no, I don't like that generator schedule, it relies too much on that generator, and what if it goes out? Then you'd say, well, but did you tell the optimization that you didn't want to rely too much on generator? And they say, well, no, but that's kind of obvious. And you're like, okay. Or you can't look at that and say, I don't like that portfolio. Why? Because it concentrates too much in this sector. And then you say, well, excuse me, did you tell it to not concentrate too much in that sector? And they'd say, well, no, but I mean, and then you're like, okay. So, I mean, you laugh, but you know what? This happens so, like right now while I'm talking, this is happening out in the world like maybe 10 or 100 times. Okay, so, okay, bad models. This is a really tricky one. So, they're never exactly right? So, the parameters are slightly off. There might be all sorts of effects in terms you didn't think. And a model could change with time, smoothly or abruptly. Something could break or something like that. All sorts of things can happen. Now, if you're lucky, everything still works well. But if not, it can be bad. So here's an example. So here is the return distribution of some portfolio. And that's a 0 here, and that's 15%. And this says that your probability of a loss is really small. And, it looks like kind of mostly you're going to earn about 7%. It's good. This is great. This is what you use optimization for. But then it turns out, your model is not quite right. And then you might get something like this. And what this says is, well, there's a small probability of a loss. OK, instead of 7 or 8%, you're making 6.5. And you're like, you know what? That's fine. I accept that, right? Now, of course, it could also be this. And this does happen. And so this says that here's 0. This says that the probability of a loss is like 85%. I mean, in fact, and the most common thing is so basically you just did a bunch of optimization, optimized a portfolio, executed the trades, and the results are not good. It's a disaster. OK, so this is roughly how it works. Now, of course, this is just garbage in, garbage out, right? That's the point. If your models or data are or become wrong, then the results are useless. And then typically, it can be much worse than useless, right? And then what happens is optimization gets a bad name in that field, right? So usually, people who've been doing this intuitively, they're often called Bob. I don't know why. But Bob has been doing this for a long time. Bob is in the back. He says, look, I've been scheduling these things. I've been making the orders from the factory for 25 years. Usually it's some young kid who's just come from, let's say, University of Washington after learning about this. And they say, no, but, we're going to do this way. And then there's a total disaster and everything. And then they throw the kid out. Bob comes back in, muttering about, we should have known better and all that. So anyway, so that happens all the time. By the way, what happens is 5 years later, a new kid comes along. She's learned a lot more, and this time it works, right? So, OK. Now, good practitioners always check if the results are sensitive to models and data. Always. Notice the qualifier good. And there's actually ways to build this directly into the optimization. So I won't talk about that. But I will just show you one picture. This is from a student of mine. This is real. I guess he wouldn't even tell me what it was from. It's some financial data. But the point is this. If I showed you this here, that's 2003, that's 2007. You would look at it and you'd say, oh, yeah, and I had a statistical model of it, you'd say, yeah, no problem, sure, yeah, that's fine. But then you can see what happens. Everything goes insane. By the way, this picture here, if you do this kind of work, this is what your nightmare looks like. It's that. When you wake up at 2 in the morning and you're dripping with sweat, that's it. Okay? And it's every time there's one of these little bumps up there, you're thinking, it's this. Oh, no. Right? So just to show you that, these are real things. Okay. Recourse. I'm going to talk about one more thing, which is, in fact, a lot of the decisions are generally made sequentially in time, and you get new information. Right? I've been talking about optimization, which is kind of a static thing. It says, assuming everything is correct, you don't get any information. And so this is the idea of recourse. And the basic idea is you make decisions over time. Right? You decide to invest or trade some things or any of these things, right? But that's based on the information available at the time. California schedules its generators based on weather predictions made midnight the night before. Okay? And are they good? They're actually pretty good, but they're not perfect, right? I promise you at 1 p.m. I can predict the weather at 2 p.m. way better than I could have the night before at midnight. And so this has got lots of names. Dynamic optimization, optimization with recourse, multi-stage optimization, automatic feedback control. That's another name for this. By the way, the people who do all these things would not recognize that they're the same thing. I'm lumping them together here. Oh, and in AI, this would be called an intelligent agent. Because they decided to make up a new word for one we already have 20 for. But anyway, it's fine. Okay. So the idea is it exploits new information, and it corrects for model errors. I mean, at some level, it's very intuitive, right? If you're running a supply chain, you make predictions about how many people are going to order something on next Tuesday in this region, and you start shipping stuff out there. The next day, you'll get updated market predictions, all sorts of other stuff. Maybe your model shows that weather actually affects how much people buy of some product. No problem. You take that new thing into account. Now, in generator dispatch, that's run with recourse. So what happens is you modify the generator powers based on updated demand predictions, right? That's what you do. In a trading engine, you actually update what you decide to do based on things like the realized performance. You have updated predictions, you have current events and things like that, and that would cause you to do different things. And in a spam filter, the adaptation is slower, but you adapt to user feedback. Because when you're running a spam filter and somebody hits something as spam, like there's a new one, very cleverly designed so it goes through, someone flags it as spam, you're getting new information and you're going to update all those weights. Okay, but maybe on a much slower rate. Okay, now the standard scheme for this is rolling horizon optimization. So what it means is, right now, what you do is you predict what's going to happen in the future. Now, in some cases, you can predict pretty well, like electricity demand. In other cases, like, say, stock asset returns, that's the whole point. You don't know. If you could predict well, ooh, you would be doing very, very well, right? So there you're just, you don't expect these predictions, in most cases, to be perfect by any means. They can even be quite bad. Then what you do is you use optimization to find a plan of action. You execute according to the plan. And then if new information becomes available, you just redo the whole thing. Right? So this is sort of the idea. And I asked someone in supply chain optimization, what do you call it in supply chain when you do this? And he looked at me and he said, what do you mean? I said, when you get updated predictions of demands and things like that, and you re-optimize the shipments and things like that. And he looked at me and he said, we call that supply chain optimization. And I was like, okay, it's like fine. So, and it's kind of obvious, right, what to do. Okay, so, and I'll do a quick example here just to see how this works. So this is generator dispatch. I mean, this is an example where it's not all of California, because all of California, you can start making good predictions. So this is something much smaller, right? So this would be a microgrid or something. So what happens is, this is where you are. And this green shows you your prediction. So you don't know that there's going to be this spike in demand. And the point here is, what you do is you show this. This is you predicting what your generator should do. That's what it's done. This is the current time. And then you propagate time forward. And you can see what will happen is up here, when you're up here, actually it's gone up, and that's your new prediction. And so you've done this, you've actually adapted to this increase. What's amazing about this is the following. If you were to see something like that, you'd say to someone, your predictions are terrible. They are not good. And the dirty secret of all this is these things work really well, thank you, even when the predictions are not that good. Right? So if you were to look at sort of supply chain optimization and say, how many people are going to order this thing in this region? They'd say 22. Right? And you might look, and historically, well, it's, it could fluctuate. But it turns out to do this kind of optimization, you win if you just get kind of the big flavor, like is a lot, is a little. OK. All right. So I'm just going to wrap up. So what it is there's really a new applied math. I mean, this is actually very important. This is actually, I hope, what you would take away from this. So it's a combination of techniques and approaches, right? It uses model fitting from data. It's often statistically motivated, but not always. And it uses an algorithmic and computationally oriented approach. In other words, you don't imagine you're going to sit there with pencil and paper and write some equations and integrate some, t squared sine t. That's very 19th century or whatever. You don't do that, right? And this is the core of this new applied math. Now, unfortunately, applied math means something else right now. Typically, if you say applied math, it means people who do the partial differential equations that come up in physics and fluid flow and things like that. By the way, this is very important stuff. So we need people to do that. So this is not supposed to be an attack on them or anything like that. So very important stuff. But this new stuff usually focuses more on the mathematics of information, not the mathematics of physics, right? So, and this new applied math is done in computer science, electrical engineering, statistics, OR. You may notice a department missing from that list. That would be math, yes. Yeah. So I do that actually just to irritate people in math. It actually works pretty well, and it's not completely, it's not totally fair, but it's not bad. OK. And so it's applied in lots of different areas. And honestly, when you talk about a smart system, this is it, right? When you look at this thing and you'd say, well, how did you know to buy only this number of shares of that? Or how did you know to flag this thing as spam? Or how did this turbine know to come on or something? Basically, it's usually something like this running behind the scenes, right? Or how could the same engine put out, how could it be a factor of like 8 cleaner than the one in your car that's 20 years old? It puts out the same, it's the same size, it's roughly the same cost. Yeah, how could it be literally 8 times cleaner? This is the answer, okay? So, okay. So one question is, why now? And, now means a couple decades, right? And the answer is something like this. What's happened is, what we've had in the last 10, you can call it 20, whatever you like, 5, roughly. We have the ability to collect, store, and move massive data. Cheap, powerful, ubiquitous computing. So, I mean, it's really cheap. And indeed, there are people working on new algorithms to do all this kind of stuff. But, these are old ideas. This goes back to the 1940s. Here's Vannevar Bush, from MIT saying, we've arrived at a point where we have cheap, complex devices of great reliability. Something good should come of it, right? That's 1940s, right? Or something, 1947. So the last question, I'm not going to say a whole lot about it. In fact, I'll say nothing about it, is where's it going, right? Well, first of all, it's not going away. So this is going to keep, it's going to keep moving forward. And it's going to just get more and more pervasive. So that's what's going to happen. And you're going to see things like, smart grid and smart appliances are going to happen, and personalized medicine and treatment. And you're already seeing spectacular things happening in all of these areas. But they're going to just, you're going to see a lot more, and they're going to be they're going to diffuse out across everything. Personalized advertising, I don't know if that's good or bad. And there'll be lots of other stuff happening, some good and some probably bad. And the question is, what's a world filled with these things going to look like? And actually, I don't know. It's going to be kind of creepy to have things follow you around and suggest things that, or as what somebody I know who did recommendation system is, we suggest things to people that they didn't even know they wanted. So, and he said, and we're often right. Okay, so I will finish here. And I would be very happy to answer questions or anything else.